because if it's thought to be a school bus, I'm going to go through and see how many school buses are near it in all these layers, and it won't look right.
What do you mean by near?
So they're just using something akin to the L2 metric on neural net node activation space. It's actually, I guess, the normalized dot product metric. And there's no reason to think that's optimal. I actually asked Nicola Paperno about that.
I mean, near in what space? Near in the image, near in...
So as the image filters its way through the neural net, right, you have a bunch of you have an activation at each node in the neural net, in each layer. And so you just take those numbers and you take dot products. Right, so it's a very naive definition of distance, and yet it works. I could imagine something more sophisticated working better, but it works quite well. So then they construct out of this in a way that I won't go into, something they call the credibility, which is meant to be something like the probability the answer is right, as opposed to what's usually called the confidence, which is the thing that comes out of the neural net classifier. And the confidence really bears no resemblance to the probability that the answer is correct. These are adversarial examples, right? These are things designed to fool the neural net. And this distribution is pretty much flat from 0 to 1. And the fraction of them that are predicted accurately are classified accurately is just, low in all cases. Whereas if you use Paperno's trick, then most of them, so that this red is a histogram showing how many examples, so most of them are given a very low credibility, and that's correct. They are incorrectly identified. A small number are given high credibility, and those actually tend to be correctly identified. So to the extent that this has slope 1, you would be happy, right? You're getting something that's like a frequentist probability that the answer is correct. So that seems like an advance. Another nice thing about DKNN is that if the neural net's making a mistake and you don't like the answer, you can ask what training examples support that answer. Why do you think that? There's a great example in the paper of Obama with his hand over his head, and there's some kind of ball you can't quite tell, and it classifies him as basketball player.
Which is true.
Which is true. Then you crop it a little differently and it says tennis player. Okay, and you can, in both cases you ask why. For the tennis player case, it shows a bunch of pictures of tennis players with their arm in the same position and a green background. He had a green background, he was wearing white. The tennis players are all wearing white. So you see the examples that support that decision. So it's nice to be able to do that. And I think this would be useful in astronomy. If you're training a neural net to do something in astronomy, this gives you a way of asking, how do you get that answer? And also, have you ever seen anything like that before? Right, because if you show it something that's rather different than what it's seen before, it might say, well, I think that's a panda galaxy, but it doesn't really look like the other pandas I've seen, so I have a low confidence, low credibility. So anyway, that's the closest I've seen to actually, something that looks like a probability that you're right. Okay, so back to our adversarial training of Madri et al. They did something more clever for specifying delta that I don't really have time for, but let me show you the results. So they trained up a new neural net image classifier in this more clever way, and now we're going to follow gradients from one class to another. Before, with the panda and the gibbon, those gradients just looked like noise. They were not semantically meaningful. Now we're going to go from turtle to bird. Okay, that's not the first thing you might think of as a bird, but it plays with your neural net a little bit, right? You have to admit that the gradient from turtle to bird is making the image look more like a bird. And that's really good news, because that means the classifier has learned about features that we might think are important, not just some crazy texture in the adversarial noise. Here's another example. Let's go from class cat to class dog. And I said class dog because you get 2 for the price of 1. And I've looked at this enough times, I could see the dog already. Right? So now we have a fully automated way of saying, take an image of something and make it look like a something else. And I think that's cool. That could be used in art, who knows. Okay, so I don't know what else I should really end. This is the famous adversarial toaster patch. That's fun. One of the things you can do if you're following gradients is you can say, find me the image that looks more like a toaster than anything. And it's that. And if you put that in any image, it's classified as toaster. Saliency maps are a fun thing. You can ask which pixels in the image contributed to the decision. That's a dog. Why? Well, those pixels say it's a dog. For the sailboat, it's not just the sailboat, it's the water it's on. So that would be a hint that the background of the sailboat matters. I don't know what you do with a washing machine. Anyway, I have a little spiel on interpreting outputs as probability, but I'm probably out of time. But if you want to know about Kullback-Leibler divergences and how they relate to this, please ask. And why don't I end? Thank you.
Well, we had very excellent talk and very question. I think quite a few of them see your face.
It's not a question, Doug. Would you be willing to give a 3-hour talk on this?
I certainly
a lot
have.
of people will come.
I certainly have enough material for 3 hours.
I know, but I think it'll be nice to have a more relaxed, interactive way of understanding.
Right. Yeah. There's really a lot we could discuss. Yeah. I'd be happy to.
So,
Sure.
try to find a time, yeah.
Yeah, any other question? Yeah, please go ahead.
Well, this nearest neighbor thing looked very nice. One of the questions I had though is in terms of when you come up with something that seems to be a mistake. So I read a paper a few months ago where a bunch of people who do AI got together and they published their unexpected results, the mistakes that they had to take out in order to get the results they were looking for. And often those were extremely interesting. Like
Right.
they were trying to minimize the number of steps a robot took to go from here to there. And one of the trials, they got 0. And it got from there to there. How did it do it? Well, it knew that it was minimizing the number of steps, so it flipped over on its back and did it with its arms. So this is something that they didn't think of. It didn't
Right.
put it into their minimization function, but you know, it was an interesting mistake.
Right.
So I guess the question is, I mean, the very important question you're addressing is how do you try not to make mistakes in the classification? But there's
Right.
another question which comes up when we're trying to apply all this stuff to LSST and finding possibly new types of transients that nobody's thought of before. How do you identify when you have a mistake that it actually is interesting, that something was discovered that we hadn't anticipated?
Yep. That's a very important question.
And it wouldn't be fair to
But,
expect you to answer
but I
that.
mean, for the first half, right, you gain trust by breaking things in every way you can think of, and then finding ways to make them robust to all those various kinds of attacks. So I think this whole field of adversarial AI is very useful for us, because there are people trying to make these robust against malicious adversaries who are doing the worst possible thing. And if they're robust to that, then maybe they'll work.
So, just a quick question about the landscape of this research. We tend to think, you know, in academia that much of the progress is coming from academia, but clearly there are lots of businesses interested in this, and the defense, you know, industry, and so forth. So, where is most of the innovation, most of the important papers on the archive coming from?
Well, it's both actually. I mean, Google Brain is doing a lot, right? And other big companies like that. But you know, MIT, Stanford, Berkeley, maybe Harvard. Harvard, of course, yes. You know, the universities are doing a lot too. So I think it's really both. I mean, the businesses may tend to focus on specific problems that are of interest to them, and the academics are free to roam randomly.
Yeah, please go.
So I'm coming back to this again to the brain analogy, because in the end what we want often is to understand the neural net with our brains, also for image recognition, for example. So, for example, I feel that often that it might be the case that you often don't get it right because of the training set that is often restricted just for your code. For example, just the street signs and roads and cars, where our brain, we learn first general shapes and colors, and then other stuff, and and all is connected. So then if you get a stop sign, you'll first notice it's red, because the red just jumping from it, but if you do a training set that is just signs, then it doesn't work that way.
Yeah, we've got a long ways to go on making these things generalize better. One thing I didn't mention is domain adversarial networks. There you have an idea where you have two neural nets that are playing a game with each other, and one is a feature extractor. It looks for the features that are going to be useful for a classification, and the other is a domain recognizer. So again, domain could be day-night, it could be horse-zebra, whatever you want it to be. There's a domain recognizer that looks at those features and tries to decide what the domain is. And so if the features reveal the domain, then the feature extractor loses. If they don't reveal the domain and they're useful for classification, then it wins. And by doing this, you can kind of project the space of all possible features you could think about into domain invariant and domain variant. And that's really important, because if you want your car to drive day, night, snow, cloudy, sunny, you want to use features that are not dependent on the lighting. And so you can explicitly force the neural net to not use lighting dependent features. And when you do that, it turns out you can often train it with fewer examples. So the better we get at that kind of thing, probably the fewer examples we'll need to train.
So
Yes, sir, Richard.
the fact that a lot of these images that the machine learning is getting wrong